Guys, so today we're going to start Unit 4, and it's going to be some applications of the derivatives going on. Okay, so some essential questions for this first one of 4.1, interpreting the meaning here of that derivative is making sure we understand the position, velocity, acceleration, and how they relate, which we've talked about, but we're going to go in more in depth, making sure we have the units. Definitely getting the interpretations now, which we hadn't done the interpretations before, so we really want to make sure that we understand those. Okay, so a derivative, again, is not talking about the second before or the second after. It is that, boom, instantaneous. It is that exact second. It is only that moment. It's like this infinitesimal sliver of time. Okay, so it's so cool. Like you're only, boom, not even that, because that was like more than a moment. Okay, so let's just have a little warm up, getting us back into the groove here. So um, if the tangent line to f of x here at some a equals 3 has this equation, can you tell me what f of 3 and f prime of 3 would be? Okay, so this is the tangent line. So basically we have some curve and we're finding the tangent line at 3. So here, if I wanted to know what f prime of 3 was, that would have had to have been the slope. And if I want to know what f of 3 was, remember they share that common point going on. And so all I have to do is plug it in because it's going to share the point here. So 15 plus 2 is 17. So that would have been f of 3. Because that is the only point that they really know that we know that they have to share is wherever we created that tangent line at. Okay. Okay, so I have this little blurb here about calculus, and I'd like for you to go ahead and read it. And you can pause me and then unpause after you have read it. Okay, so when we are talking about this motion, a lot of times we're going to use a particle is moving along the x-axis. So here's like a particle, and you can see how it is moving along the x-axis. So it may be slow, it may speed up in the positive direction, it may speed up in the negative direction. But right now, when we talk about a particle moving along the x-axis, that little yellow dot is the particle, and we can see how it's kind of moving. So we're going to have direction with our the velocity, the speed is going to have direction to get us to the velocity, and we're also going to have acceleration that we're going to be looking at. Okay, so that's what we're talking about, and a lot of AP questions are going to begin with a particle is moving along the x-axis. So here, if you kind of read this one, we're not going to solve it. I want you just to read it though. And if you see, it starts, hey, for this time greater than 0, a particle moves along the x-axis. So that's what we're thinking of, is that little yellow ball kind of going back and forth. And then we're going to go and we'll figure out how to answer these questions. Okay, so it is almost certain that on your AP calculus exam, you're going to have to interpret what a derivative statement means in the context of the problem. So we really want to make sure that we have that. I'm going to kind of take us through some of the good and the bad ways of interpretations. So here's the prompt. The differentiable function v of t gives the volume of water measured in gallons in a tank at time t. T is measured in minutes, so v of t is the volume. Explain the meaning of v prime of 5 equaling -6. So again, we have this tank, whatever it is, I don't know. It's being filled up with water, okay? And so we're talking about the volume of the water here going on. And we're calculating the time as it's moving in minutes. And I want to know what this v prime of 5 equals -6 is. So actually, if I have a negative, what's that water having to do? Is it increasing or decreasing if that derivative is a negative? Well, again, that's giving me a direction here. That is decreasing. The water is going down. So it's starting and it's going down. So somehow the water is leaving the tank. And what time are we talking about? We are talking about time equals 5. This is how the volume is changing. And I always use the little triangle to denote changing. So here are some things that we definitely can think of. Oh, and if we're on a first derivative, before we get down here, we're on a first derivative, if this is the volume, and volume is, and I should have highlighted that, gallons, right? So this is in gallons. If we're talking about this change here, then this guy's going to have to be, again, that's like a velocity in gallons per minute. Okay, so as we kind of want to interpret, we need to know the time. We need to know that this is going to be in gallons per minute. We need to know that this is the change in the volume. Okay, so let's look through some good things that we could say. And actually, I have seen where this is not good, and this is from AP. It's not after 5 minutes. If you're going to say after 5 minutes, you need to say 5 minutes after time equals 0. So I won't include this. So we're going to say at, okay? And make sure you really see that. I know that AP created this, but I've also seen where AP has said, no, after 5 minutes could be after 5 minutes from time equals 20. Okay, and that's not what we're looking at. If you're going to say after 5 minutes, you need to say after 5 minutes from the initial time. But it's easier if you just say at 5 minutes, the volume of the water in the tank. And here, if we say the word decreasing, that's to get that negative, then we can't include the negative again. Because if you said decreasing at a rate of -6, then you've got a negative negative. So this is decreasing at a rate of 6, and then they have the gallons per minute. So they've told me the time. They've told me what we're talking about. If we say decreasing, then we have to say 6, and they've got the units. Okay. Here, when 5 minutes have elapsed, okay, so elapsed from the beginning, okay, the amount of water in the tank, that's talking about the volume. And here again, they're saying going down at the rate. So if they're saying going down, then we got to make sure that this is positive again, and they have the units. So all of these are okay. This is probably the one that I would do right here. Or actually, I would say instead of decreasing, I'm going to tell you what I would say, but hold on, we'll read it. Mine's closest to this one of the ones that they like. Okay, the amount of water in the tank, so that's the volume, is decreasing at 6 gallons per minute at t equals 5. So they have the time, they have the units, they have that 6, and they didn't put the negative because they put decreasing, and they're talking about the volume. So what I would have done is I would have cheated here. Instead of saying decreasing, I would have just said changing, and I would have left the -6, changing at the rate. Okay. So, and here they're saying that at the rate is not necessary since we have the units, but I would have liked it. So right here, if I was to write, I'd say the water in the tank is changing, and you could leave decreasing at a rate of -6. So if I just said changing, I would leave the -6. If I said decreasing, then I would put 6. gallons per minute, and I've got my units at T equals 5 minutes. So don't forget, oh, don't forget Tom's Cyber Weekend. No, don't forget that you need the time. You need to interpret this with the units, and be careful if you say changing with the negative or decreasing without the negative. Okay, so some bad things. After 5 minutes, the amount of water is changing at a rate of 6 gallons. So if they say changing, then I need to have had the -6. After 5 minutes, the instantaneous rate of change of the water in the tank is -6 gallons per minute. So this is okay. Actually, they don't like it if you're gonna like interpret because they just said changing, but this one is actually okay. The only thing I don't like is the after. I would say at. And so this is, yeah, that one was just they were saying is awkward, but acceptable. These are the wrong, sorry. After 5 minutes, which again, I would have preferred the at 5 minutes, the rate of change of the water in the tank is decreasing at 6 gallons per minute. So this is saying, this is giving you the acceleration. So if they said the rate of change of the water is decreasing, so do you see that? They're basically saying that the volume is decreasing. That's an acceleration. So that's not true. It's not the rate of change of the water, it's just the water is decreasing at this rate. So hopefully you see that difference. So we don't want to get to that second derivative. We want to keep it with the first derivative. So that's what they did here, which is wrong, is they said the rate of change of the water, not the volume. Here at T equals 5 during the next minute, so they've got this whole next minute going on, and that's definitely not right. We need the instantaneous, okay? Okay, so, um, and you can go ahead and read through this, but we're gonna look at this example. If we said V of 5 equals 6, then this is talking about the volume at T equals 5 is 60 gallons. T equals 5 minutes, sorry. This one, if we kind of see the difference, this is talking about the velocity now. So the volume is changing at the -6 or decreasing at a rate of 6. And now we have gallons per minute because we are in the velocity. So make sure that we know that it's the volume that's changing. So here I'm going to give you this prompt and I want to see if you can write the interpretation of what this is asking. So the differentiable function c of x, where c is measured in dollars, gives the cost of digging a hole that is x is in feet deep. So I want you to explain the meaning of this guy right here. Now I'm going to tell you, actually, I'm going to take you through this. I start at the time. So I'm going to say, hey, at, and it's actually not t here, it's at the x. I start with what this value inside is. So at x equals 20 and x is in feet, okay? So at x equals 20 feet, what is C now? C is the cost of digging a hole. So the cost of digging a hole, and the cost is in dollars. And here it says is 55. So I'm just going to say is changing, oops, at a rate of 55, and then we need to put that this is dollars per foot. Okay? All right, you try the next one. actually try the next two. And go ahead and pause me and try them, and then we'll talk about them together. Okay, so here, h of t is now the height of a rocket in meters, and now time is in seconds after launch, and I want to explain this guy right here. So I'm going to start with this. At t equals 20, and that's in seconds. And then h is the height. The height of a rocket is changing, keep forgetting that G, at a rate of 510, and this was in meters, per second. Okay, and go ahead and try the last one, which I think you did. Okay, so this is now the number of bacteria. T is in minutes, and I want to know this. So at t equals 12 minutes, the number of bacteria in the Petri dish, which, okay. And you can say is increasing, okay, if you want to do it, this one is increasing at a rate of 720 bacteria per minute. So it's okay to use changing, or it's okay to use increasing and decreasing. Okay, so I want you guys to look through 1 through 6 here and see if you can do that. And then when you're ready, unpause me and check. So pause. This one, number 1, is the average rate of change. Number 2 is an instantaneous rate of change. At noon, instantaneous. During the first 5 minutes, average. Over the 12 hour is the average. And when t equals 7 is an instantaneous. So this is just helping us practice whether or not we know we're doing the derivative, or we're doing like the slope of a secant, where it's just change in position over change in time. So remember, an average rate of change is change in position over change in time. An instantaneous rate of change is the first derivative of the position, which is a velocity. Okay? All right, next one. Oh, yes, matching. Go ahead, see if you can match. Pause me, and then unpause me when you're ready to see. This is fun. Okay, so we're going to go through, and I'm going to give you the answers. And if you want to ask me questions during class, then you can. All right? Hopefully you did good. I love the matching, I think. Okay, this next one I would like to do in class together to check through with you. Okay, so just remind me that we're going to do this one in class. And now we're going to go to an AP example. We have done the approximation of this. This one should be easy for us. But now I want us to be able to interpret. Before I said, hey, it's bonus if you can interpret. No longer the case. Now we have to interpret. So let's first start with that approximation for h prime of 6. So 6 would be in between 5 and 7. So we're going to use the average rate of change to approximate that instantaneous rate of change. And you can leave it like that, but we have to have correct units. So change of h was in meters. Change of t was in years. And remember, you do not have to simplify. If you did, that's 5/2 meters per year. but you do not have to. So now we want to start with the interpretation. So again, we're going to look at this, start with that inside. So at t equals 6 years, and what is it that h is? H is the height of a tree. So the height of a tree is, and in this case, we could say increasing, or you could say changing, whichever you like, is increasing at a rate of, and you could leave it like this, meters per year. Okay? Or you could simplify it. Okay. Next one, I want you to go ahead and read through, pause me, and see if you can see what you want to do for B. When you're ready, unpause. And this is a calculator allowed. Okay, so hopefully you paused me and you're ready to unpause. So now it wants us to go find this first. Well, we're not approximating it like we did a second ago. Here we were approximating or estimating. We're not doing that. We actually have to find it. So here is f, and so since I have a calculator, I'm not going to go take that derivative by hand. I am going to use Math 8, yeah, in my calculator to get my answer. And remember, we need to go to 3 decimal place accuracy, so you could have either truncated it or rounded it up. Okay, so you could have truncated it like that, or you could have rounded it, whichever. Or you could just go out to 4 decimals. All right, if you need help with that Math 8, let me know, but make sure you get this. And we're going to have to use units, so let's go ahead and look through. What did it say f of t is? So f of t here is let's see, we have the pounds of bananas, and customers are removing bananas. And what's t in? Okay, pounds per hour. So this is actually, f of t is measured in pounds per hour. So is this right here, is this a velocity or acceleration or a position? So this is a rate. This is a velocity going on. So now when I go to interpret ours, what we just found would be in pounds per hour squared. So now we're interpreting an acceleration, not a velocity. So here, I know that the acceleration at t equals 7 hours is decreasing at a rate of 8.1195 pounds per hour. And I messed up. I'm like reading this now. The acceleration of bananas. Did I spell that right? B-A-N-N. B-A. Did I spell that right? B-A. Now. Okay, hold on. I gotta spell bananas right. B-A-N-A-N-N-A. Okay. The acceleration of bananas being removed. Things that are hard for Miss Whitmer. Spelling bananas. So make sure we have that part. And then that's decreasing at a rate of the 8.1195. Or you could have said changing, okay, at a rate of this. So we need to make sure that like we have what we're doing here, like the acceleration. Let's see. I actually messed this one up. This would be the velocity. I'm like looking at it. So the velocity of bananas being removed at t equals 7 is decreasing at this rate. Yeah, sorry, just like before it was the volume. So this is an acceleration, but it's the rate of the velocity. Yeah, give me a second. I'll get in my groove here. Sunday afternoon. Okay, so the velocity is what's changing at this rate, and that gives me acceleration. Okay, or you could have said the acceleration of bananas. Dang it, I did it again. B-A-N-A-N-A-N-N-A. Of bananas being removed at t equals 7 hours is that guy right there. Okay, squared. Ah, shoot. You guys, what is wrong with me on this problem? I forgot the squared up there. Make sure you have the squared because you are now getting an acceleration. Okay. Roll with me on that? We'll talk about it more. And then let's go ahead and do part C. Try it and then pause me. Okay, so hopefully you are ready to unpause me. Let's go to orange here. So here, this is the customers removing, and then this is the employees adding. So we have two things now going on, and they are both rates. So this is what I call a rate out, because they're getting removed, and this is what I call the rate in. And later we're going to deal a lot with that, rate outs and rate ins. So the overall rate is the rate in minus the rate out. So we want to like kind of see that like that's our overall rate of how the bananas are changing because we got customers adding or customers taking, we got the employees adding. So what's the overall rate? It's the rate in minus the rate out. So the rate in was, what was the rate in? Was G of t, and the rate out was F of t. So if I want to see my overall rate at what time 5, then I need to do G of 5 minus F of 5 in my calculator. And we have two possibilities. We can get a positive or a negative. If I have a positive, then I know that we are increasing overall. If I get a negative, then I know that I am decreasing overall. So I want you to plug in and see what you get. Okay. And here I got a negative, and so I know that the bananas are decreasing. Go ahead and see if you get that. Okay, last two. Go ahead and see if you can get these on your own. When you're ready, unpause me. See if you get B and C. Okay, so that's the end of this first lesson. Anything you want to go over together, we can do in class. Try to make me smaller. That was nuts. Okay, see you soon.